record. Okay. Perfect. All right. So good morning, everybody. What I will do first is that I will review some of the concepts, which I think are very important, and then we will cover new material today. So first, assume that two items are taken from this set without replacement. And basically, the difference between ordered and unordered is clear in this example. So ordered means AB and BA are two different members, but unordered means that, you know, order doesn't matter. So instead of both AB and BA, we only have one of them. So we talked about three counting techniques: multiplication, permutation, and in permutation, we covered subset permutation and similar item permutation. And we finally talked about combination. So for the case of multiplication, the example that we gave was how many watches with three band types. So first option is band type, second option is screen size, and the third option is color, right? So since we have to pick all of these, there's an and between them, we have to pick band type and screen size and color, then we multiply. Next up was permutation. So in permutation, order is important. So how many three-digit numbers with 5, 6, and 7 can be made? So here in permutation, we don't allow repetition. So 5, 5, 6, for example, is not allowed. And the answer is basically 3 factorial, right? It's n factorial if you have n digits. We also talked about subset permutation. So here we have more number of digits. We have 1, 2, 3, 4, and 5 digits. And we want to create 3-digit numbers, right? So the answer was, the answer for that, we've actually proved it in the first class, was 5 factorial divided by 5 minus 3 factorial, right? And if you forgot how we proved it, it's very important. You can go and look at it again. So I think it's important, but the proof is not necessarily for this course. So the answer is 60, right? So basically the equation was n minus p factorial, right? And then we covered similar item permutation. So here we have 3 5s, 2 6s, and 1 7, right? And we want to count how many permutations we have. So the answer is, we basically count how many numbers we have here. So we have 3 5s, so 3, 2 6s plus 2, and 1 7 plus 1 factorial, divided by each one of those individually factorial, right? And the answer will be 60 in this case. And at the end, we talked about combination. So in combination, order does not matter. So how many ways we can pick 11 players from a class of size, let's say 101, right? And we don't care the order in which we pick those 11 players. In this case, the answer is basically n choose p, right? Which is n factorial divided by p factorial times n minus p factorial. And remember that combination is always less than or equal to subset permutation, right? Because in subset permutation, order does matter. So subset permutation and combination are in fact quite similar. The only difference is that in combination, order is not important. So if we have 3 sets and we want to calculate the probability of the union, then this is the equation for that. And the reason for this is clear from the Venn diagram, right? So let me, I see there are 7 people on the waiting room. So let me, okay. All right, sorry about that. So here, to find out the probability of the union of three sets happening, right? For example, set A can be like, the question could be like, we have a deck of cards, we are picking a card, right? And set A can be the card is a heart. Set B can be the card is an ace, and the set C could be, that the card is basically a king, right? So the union, to calculate the probability of union, we add individual probabilities, but similar to two sets, here what happens is that we count some outcomes multiple times, right? Because of that, so if we have three sets here, A, B, and C, A, B, and C, what happens when we count is that we count the basically intersections too many times. So we subtract the intersections, and then after we subtract the intersections, what happens is that we subtract the innermost intersection, which is this part, too many times, which means that we don't actually count this part at all. So to correct for that, we add the basically subset of all sets, the probability of subset of all sets. And note that the signs alternate. So first we have positive signs, then we have negative signs for two sets, and again for three sets we have positive signs. Okay. So if the intersection between the sets is zero, meaning that if the sets are pairwise mutually exclusive, all of these terms cancel out, right? So to find the probability of union, that's an easy case. In this case, all we do is we just add up the probabilities, right? And the Venn diagram for this case would be something like this. So sorry, it's not called A, it's called E1. So E1, event 1, event 2, event 3, event 4, right? And so forth. So these events are mutually exclusive, meaning that no two of them have any overlap, right? And in this case, you can simply add up the probabilities without worrying about counting the intersections too many times. So the next concept, which is a very important concept, I really encourage you to, solve all of the suggested problems and even more on conditional probability, because it is a very, could be a very counterintuitive concept. And the only way you can master it is by solving many questions. And, way after midterm, we keep talking about conditional probability. So it's very important that you learn this topic. So P of B given A is defined as the probability of B given that A has already happened, right? So as an example, we have a communication channel which has an error rate of 1 per 1,000 bits, right? So that means that errors are rare, sorry. So that means that errors are rare, but they do tend to occur in bursts, right? And that means that if a bit is in error, there is a high chance that the next bit is also in error. And that chance is more than, the 1 per 1,000 bit, right? So that means that if we know that the neighboring bit was in error, then the chance of the current bit being in error is higher than 1 over 1,000. And the way we calculate it is using this equation. So P of B given A is P of intersection divided by P of A. So P of A, remember that P of A is the number of outcomes in A divided by N. We divide by N because anything can happen when we write P of A. Similarly, P of A intersection B is the number of outcomes in A and B, again divided by N. And N here is the total number of samples in the sample set, right? But when we write P of B given A, that means that A has already happened, right? So we divide that by the number of outcomes in A, right? So what do I mean by that? I mean that if this is our sample set S and it has N members, right? So S has n members, and we have set A here, and if I have set B here, when I write P of B given A, that means that for sure one of the outcomes here has happened, right? So for sure, nothing here could have happened outside of A, right? And because of that, we divide by the number of outcomes in A, right? So it will become clear by examples. Don't worry if you didn't understand my explanation. So we will do many examples of conditional probability. So let's say that, again, I go back to our running example of rolling a die. Let me, there's more people in the waiting room, so let me admit them. All right, sorry about that. Okay, so so S is a sample set from the experiment of rolling a die, right? So I'm rolling a die, and the number that I can get is 1 to 6. Now, suppose that I set B to be the set of even numbers that can come up, right? 2, 4, 6. So probability of B is 1 divided by 2 because B has 3 members and S has 6 members. So 3 divided by 6 is 1 divided by 2. Now assume that I define A, set A as basically getting a 1 when I roll a die, right? So here P of A is simply 1 divided by 6 because A has 1 member, that's 1, and S has 6 members. Now, when I want to calculate P of A given B, according to the equation, that's P of A intersection B divided by P of B, right? And P of A intersection B is equal to, so what is A intersection B? Actually, that's 0. So P of A intersection, A and B do not have any intersection, so that's an empty set. P of an empty set divided by P of B, and that is 0, right? So in the next line, we define set C as getting a 2. Now I want to calculate P of C given B. Again, I use the same equation as above. So that is equal to P of C intersection B divided by P of B, right? So C intersection B is only 2, right? So P of getting a 2, set 2, divided by P of B, right? So here, when I'm writing P of set 2, note that this is not a conditional probability. I'm just writing P of 2, right? So P of 2 getting a 2 is 1 divided by 6, right? 2 is a number. The chance of getting 2 is 1 divided by 6. P of B is, we calculated it before. P of B is 1 divided by 2. So divided by 1 divided by 2, and that's 1/3, right? So that's one way of solving this question, P of C given B. There's another way to solve this question. And the other way entails using the definition of, so I'm going to basically solve it here in this box. So P of C given B is, oops, did I lose all of that? Yeah, I guess I did lose all of them. Oh no, okay. So P of C given B is equal to number of outcomes in C and B divided by number of outcomes in B, right? So here the important thing is that I write in B because I know that, you know, when I divide by the total number, I know that B has already happened. So I divide by B, and that is going to be equal to, so number of outcomes in C intersection B, that's only 1 outcome, right? And number of outcomes in B, B has 3 outcomes, right? So 1/3 and we arrive at the same answer, 1/3. Okay, so let's look at another example. So here we want to write the conditional probabilities given the table below, right? So we have two features for some parts. So the feature one is surface flaw. So parts either have surface flaw or they don't have a surface flaw. And the second feature of the parts is whether they are defective or they are not defective, right? So in total, I have 400 parts, and they are basically classified into these two features using these four numbers, right? So these four numbers, 10, 18, 30, and 342, tell me everything that I need to know about this basically problem, right? So now we can calculate all probabilities that we want just from these four numbers, right? So for example, probability of failure, surface flaw is 40 divided by the total number. Probability of defective is 28 divided by total number, right? 400. Now, when I want to calculate probability of defective given failure, the equation is D intersection F divided by F. So I look at D intersection F, that's 10, right? So probability of D intersection F is 10 divided by 400. And we already calculated probability of F, that is 40 divided by 400. So the answer is 10 over 40. We can solve this using another approach, which is perhaps faster. So here I can say P of D given F is a number of outcomes in D and F. So the number of outcomes in D and F is 10 divided by the total number of outcomes in F, right? So total number of outcomes in F is 40, right? So here, basically to write this answer, I didn't use the, this equation. We can calculate all probabilities, similarly. So I encourage you to, perhaps a good practice would be to block the solution here and see if you can solve all of this yourself. Okay, so I mentioned in the first class that trees are a very good, are very good tools to solve probability problems, right? Because they give you a visual way. So we can solve the exact same question using this tree graph, right? So here at the root, I have two outcomes. Either I have a surface flaw, which means 40 parts out of 400, or I don't have a surface flaw, F prime. So 360 divided by 400. So perhaps we can write here that this represents, this path represents flaw, surface flaw, yes, yeah, 40. And this path represents no surface flaw, F prime, right? And at this node, again, I have two options. Either my part is defective, so the number of defectives are 18 when I'm in F prime, divided by 360. So that's the probability of, so here, this is the probability of defective. Right. So if you, there's more people here, let me admit. Okay. So if you phased out for any reason, I really encourage you to pay close attention now, because this is very important. So go back. So here, this number, in fact, all of these numbers are conditional probabilities. This is a source of confusion. Things stop making sense if you don't get this point. So when we are at this node, it means that we don't have a surface flaw, right? So here it means F prime, and here it means F, right? So this node, it means that we already don't have a flaw. We are sure about that, right? So this number that you see here is not the probability of D prime. This number is the probability of D prime given F prime, right? And this number similarly is the probability of D given F prime, right? Because this node, it means that F prime already happened, right? That's very, very important. Similar for, oh, did I make a mistake? So yeah, I called this also, I called both of these F prime, which is incorrect. So this is F, sorry. These, all of these here are correct, right? So this path means failure and this path means no failure. So again, this node, it means that failure did already happen. Sorry, flaw did already happen. So these parts all have flaws in it, right? So similarly, this number is probability of defective given flaw, right? And this number down here is the probability of non-defective given flaw, right? So very important to remember that when you draw these trees, the probabilities that you show here are all conditional probabilities. So now it's the perfect time to talk about independent events. So events are called independent if they are not affected by each other, right? For example, when we toss a coin, each toss is an isolated effect from the previous toss, right? So one flip does not affect the outcome of the next flip. And the chance of getting heads or tails is always 50%, right? So flipping a coin, different outcomes of flipping a coin are called independent events, right? So what is a dependent event? So assume that we have a bag of marbles, right? And inside we have 2 blue marbles and 3 red marbles, right? So the chance of getting a blue marble is 2 in 5 because we have 2 blue, right? But the point is that after picking the first marble, depending on the color of the marble, the chance of getting a blue marble in the next trial does change, right? So here, remember that this is without replacement. Meaning that we don't place the marble back, right? So the outcome of the next draw will depend on the outcome of the previous draw, right? Because it changes our sample space, right? So here, the second draw and the first draw are not independent events anymore. So we want to calculate the probability in this question that we saw. We want to calculate the probability of drawing 2 blue marbles, right? And we are doing without replacement. In fact, I solved this in the previous class on Wednesday. So I will solve it again here. So again, the tree can really help us here. I want to calculate the probability of drawing 2 blue marbles, right? So I say, okay, this is my sample space. My first marble can be blue. The chance of that is 2 divided by 5, or it can be red. The chance of that is 3 divided by 5. I'm interested in this part. Now, if I'm here, the chance of drawing a blue is 1 divided by 4 because I have 1 blue among 4, right? So remember that this number is a conditional probability, right? So this number, very important. This number is the probability of second marble blue, given that, so it's a conditional probability, first marble blue, right? Always keep that in mind, that when you draw these trees, these numbers, all of them represent conditional probabilities, right? And we know intuitively, to find the probability of this and this, what we have to do is to multiply these probabilities, right? 2 divided by 5 times 1 divided by 4. So the probability of drawing 2 marbles without replacement is 1 divided by 10 in this case, right? So this basically, this equation is a very famous equation, and I really encourage you to remember this by your heart because it's a very important equation. And this is the multiplication rule. This is a multiplication rule for probabilities. So extremely important. I can't overemphasize how important this equation is. P of A intersection B is equal to P of B given A times P of A, or P of A given B times P of B. Whichever you want, you can use either this or this, right? In most problems, only one of them works, right? So if you try to solve with the other one, you will be stuck. You can't really proceed anymore. And remember that this equation is different from an equation that you might have in your mind that, oh, P of A intersection B is equal to P of A times P of B. So these two equations are different. And the reason is that the equation below is actually incorrect, right? So this is a very common mistake that many people make, not just in the course, but this course is a very important course, in my opinion, in your life. And often people make mistakes, in their calculations and assume this equation, which is actually incorrect. This equation is correct only if A and B are independent, which is, usually uncommon because A and B usually are not independent. So we will talk about this equation later on, but it's extremely common for people to use this equation when they shouldn't. Okay, so basically don't use this equation because it's only correct in limited number of cases. Always use this equation because this equation is always correct. Okay, so the probability that a part made in the first stage of a machining operation meets specification is 0.9. So we denote A as the probability that the part meets specifications in the first stage, right? So P of A in this case is 0.9. So A is meets specs in first stage, right? And P of A is 0.9. The probability that it meets specs in the second stage, given that it meets specs in the first stage, is 0.95. So P of B given A. So the question clearly says given that, right? So that means that B, which is probability that it meets specs in the second stage, given A, is 0.95, right? What's the probability that it meets both stages? So the question wants P of A intersection B. Here we have to use P of B given A times P of A. We can't use the other equation, P of A given B times P of B. Why? Because we don't have P of A given B, right? What's the probability that the part meets the first stage, given that it met the second stage? We have no idea. In fact, we will learn in this course how to calculate this later on, but it's difficult to calculate this. We have to use the Bayes theorem to calculate this. But at this point, we don't know how to calculate this. So we use basically the other way around. P of B given A times P of A. We simply multiply these two numbers and we get 0.855. See what time it is. All right. So let's look at another example. We have a batch of 50 parts that contains 10 made by tool 1 and 40 made by tool 2, right? So it's a good idea always to summarize the problem graphically for yourself so that you look at your picture and you see what's going on. So tool 10 by tool 1, so 10 by tool 1 and 40 by tool 2, right? Two parts are selected randomly. What's the probability that the second part comes from tool 2, given that the first part came from tool 1, right? So immediately when you say, given that the first part came from tool 1, it's a conditional probability. And when you say given that, it means that this thing already happened, right? This is very important. So it means that the first part, we know that the first part came from tool 1. So what you can do, you can immediately draw your picture again and say, since the first part came from tool 1, now I have 9 parts from tool 1, and I still have my 40 parts from tool 2, right? So what's the probability that the second part comes from tool 2? So here I'm basically removing a part. What's the probability that the second part came from tool 2? And that's going to be, I have 40 parts from tool 2 divided by 49, right? So you can see it's the same probability here. Now, in the next part B, I want to calculate what's the probability that the first part came from tool 1 and the second part came from tool 2. So in this case, we are simply interested in the intersection of event 1 and event 2, right? So we basically, for this, we use the equation that we provided before. So this intersection is equal to probability of E2 given E1 times probability of E1, right? I believe this equation is in the crib sheet, but it's a very easy equation. I encourage you to memorize it. So probability of E2 given E1 times probability of E1. We know probability of E2 given E1, we just calculate it. Probability of E1 is also a simple probability because here, what's the probability of picking from tool 1 from this set is 10 divided by 50. I have a total of 50 parts here, right? So 10 divided by 50 times 40 divided by 49, sorry. So that's the final answer. Okay. So let's look at this example that we saw before. So here, again, we have the same problem, surface flaw or defective features. So we calculated these before, right? So let's look at basically, let's make sure we actually know these probabilities now, right? So what's the probability of defect given flaw from this graph, right? So once I see flaw, given flaw, I know that I have to go and look at the node that basically tells me that the part is basically the part has a flaw. So flaw is actually here. So once I see given that, I immediately come here and I say defect. So defect, yes. So that is 10 divided by 40, right? What's the next one? So now what I want to calculate is I want to calculate the probability that my part is defective and also has a flaw, right? So probability of the and flaw is going to be P of D given flaw times probability of flaw, right? So remember, again, we are using the multiplication rule, very important equation. So we just calculated P of D given F, that was 10 divided by 40. And now what I need to do is multiply that by P of F, and I know P of F was 40 divided by 400, right? So that's the answer. Probability of defective and flaw. Okay. All right. So let's look at one more example. Here, we are picking 4 items without replacement. we want to calculate the probability of the first item being blue, right? So that's an easy case. Probability of the first item being blue is 5 divided by 11, right? Because I have a total of 11 parts. Now, the probability of the second marble being blue and the first marble being blue. Now, in this case, I'm going to write this using the multiplication rule. So that's P of second blue given first blue times probability of first blue, right? So here, probability of first blue, given the probability of first blue. So when I want to calculate this, I have to change my basically sample set because I know that the first item is blue. So that means that now my bag has 4 blue and 6 red, right? So when I calculate this, I look at this now and I say that's equal to second blue. So that's 4 divided by 10 times first blue. I already calculated it. This 5 divided by 11, right? So notice that we always, for ANDs, when we are interested in multiple events happening together, we have to use the multiplication rule. So yeah, I can see that there are some questions. I see a few raised hands. What I like to do just today is I like to basically cover the material, and we will have time at the end of the lecture today. So I will answer the questions at the end. So please, I really like questions, but because I want to share this video, I don't want to name names, during this video, so that privacy is, your privacy is not infringed. Okay. Okay. So now I'd like to solve a very interesting question. Again, if you phased out, because we have covered a lot of material already, I encourage you to pay attention, because this is a very, very counterintuitive question, and it's interesting to talk about it in conversations. So the question is, right now there are around 100 students in this class, right? We want to know what's the probability that no 2 persons share a birthday, right? So we know that there are 365 days in a year. We want to find out the probability that no 2 people share a birthday, right? So the way I'm going to solve this again is using the multiplication rule. So I'm going to say probability of no 2 share birthday is equal to, right? So basically what I'm going to do is I'm going to say the first person can be born any day of the year, because that day, is free. It will not coincide with anybody else's birthday. Now the second person, instead of 365 days, has 364 days, because one day has already been used. So the first person can be used any day. So 365 divided by 365. The second person has 1 less day. So 364 divided by 365. The third person has even 1 less day, because 2 people have already been born in 2 different days. So here it will be 363 divided by 365, right? And so this was the first person, this was the second person, this was the third person, and we have to keep going all the way dot the 100th person, right? Divided by 365. So this is the 100th person. So for the 100th person, 99 days were already used, right? 99 people have already been assigned to 99 days. So here I have to write 365 minus 99, right? Which is 266, right? So that's the answer. You know, it's basically multiplication of 100 numbers, and the first number is 1, right? So I really wish we were in class, because we always get a poll about what this number is, you know. Our intuition is very poor when we multiply many numbers. So all of these numbers are relatively close to, sorry, all of these numbers are less than 1, right? Except for the first one, which is 1. All of these are a little bit less than 1, right? So this is less than 1, this is less than 1, and the last number is also less than 1. It's more than half, but it's less than 1, right? So, you know, we think that, yeah, this is a small number, maybe like 1/10, or like the numbers that I get from people just guessing this number is like 1/10, 1/5, you know, even some people say 1/1000. But it turns out this number is almost 0. It's a very, 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 very small number, right? So in fact, I will share a code with you. You can write a simple code, you know, it's a multiplication code. You can calculate the numbers, any number that you want. So here's a graph that shows the probability for different number of people. This is from Wiki, right? So if I have, so in this class, we have 100 people. If we had 23 people, the chance of having 2 people sharing a birthday is 0.5, right? So that is already counterintuitive. If you're with 23 colleagues, there's a 50% chance that 2 people among the 23 share a birthday. I'm sure that's very counterintuitive to you, right? Because 23 is not that large, right? The point is that if you go to large numbers, such as 100 in this class, the probability of sharing birthdays is 1. The probability that we calculated was the complement of that, no 2 people sharing a birthday. And that probability is 0, right? So in a class of size 100, for sure, at least 2 people share a birthday, right? And I really do put my own money, you know, if gambling was legal, I would give, you know, $1,000 to everybody in the class if no 2 people shared the birthday, because for sure that's impossible to happen. And, you know, just because of the publicity buzz, in fact, there was one challenge like this. So a few years ago, I think, yeah, 2013, Warren Buffett had a challenge that anybody who can predict the March Madness in NCAA perfectly will basically, the prize is $1 billion, right? So the idea is that there are 63 games. And if you guess randomly, you know, which team is going to win each one of the 63 games, the probability is 1 divided by 2 to the power 63. And that's a very, very, very small number, right? So there's 18 zeros in front of it, because 2 to the 63 is a huge number, right? We often don't understand how small this number is. So I will give you perspective. So the entire population of the world is less than 10 billion, right? So that's 10 to the power 10, right? That's the entire population of the globe, right? So even if I multiply 10 to the power 10 to this number, right, times 1 divided by 2 to the 63, I still get a very small number. I still get 1 divided by 10 to the power, actually 9 times 10 to the power 8, right? And that's small, still a very, very small number, even when we multiply it by all the people in the board, right? So small numbers, when they multiply by each other, they really compound. So another very useful equation is, often we want to calculate the probability of B, right? But calculating the probability of B, you know, directly is very hard. So what we do is that we divide B into 2 parts, B intersection with A and B intersection with A prime, right? And we say that since A and A prime do not have any overlap, by definition, they are complement of each other. And then when I want to calculate probability of B, I calculate probability of this, and then I calculate the probability of this, and I add them up, right? And this is a useful equation, very useful equation indeed. So let's look at this example. So so the level of contamination, you know, in some, let's say, a communication channel, or is it a, no, I think it's a part that, you know, has two different levels of contamination. The part could either have a high contamination or, you know, a low contamination, right? So the probability of the part having a high contamination is 0.2, and the probability of the part not having high contamination is 0.8, right? And we see that these two numbers add up to 1, right? So in the top case, if we have high contamination, P of failure given high contamination is provided is 10%. So if the part has a high level of contamination, there's a high chance that, you know, it fails. And if the part doesn't have high contamination, probability of failure is 0.005, right? The question wants the probability of failure, right? So remember here, we have probability of failure given high and probability of failure given low, but we are interested in an overall probability of failure, right? So what we do is that we use the equation from the previous slide. We say that, okay, this is failure. Failure can happen for two reasons. It can happen either because I have a high contamination, or it can happen because I have a H prime or low contamination, right? So what I'm going to do is that I'm going to add these two parts, right? I'm going to say probability of failure is this probability plus this probability, right? So let's first calculate this probability. Probability of failure and H prime, so this part. Here I will use the multiplication rule. So probability of failure and H prime is equal to, so I'm calculating this, probability of failure given H prime times probability of H prime. And that is basically this number, 0.005 times 0.8. And the answer is 0.004, right? So this probability here is 0.004, right? And similarly, we calculate the probability of F and H, and that probability is higher, 2%, right? So the total probability of failure is simply the sum of these two, because we can have failure either because of having high contamination or when we don't have high contamination, right? So probability of failure is the summation of these two. So probability of failure, as I said, is the summation of those two terms, and it's 0.024, right? So here I use the basically, I broke F, failure, into two parts, either high contamination or low contamination. All right. And we can extend that to many, many sets, right? So here, to calculate probability of B, we might be forced to calculate probability of B intersection event 1 plus probability of E intersection event 2 and so forth, right? But remember, it's important that these events, E1 to EK, are mutually exclusive, right? Remember, mutually exclusive means that they have zero intersection, right? So if you look at E1 and E2, they don't share anything. Their intersection is an empty set. Similarly, E2 and E3, right? So now no two of these four events have any intersection. Okay, so the example for that would be extremely similar to the previous example, right? So all we did here is that instead of saying that the level of contamination is, you know, either high or low, we added a medium category here, right? So I'm saying that the level of contamination is either high, medium, or low, right? So again, if I draw the Venn diagram, it would be something like this. So I say failure can happen either because I have high contamination or medium contamination or low contamination, right? So I basically have to add up these probabilities, right? So let's calculate one of them, for example. Let's calculate this one, high, right? So probability of failure intersection high is, I use the multiplication rule, probability of failure given high times probability of high. So probability of failure given high is this number, 0.1. Probability of high is 0.2, right? So 0.1 times 0.2, that's 0.02, right? So similarly, I have to calculate this, and I add them up and I get the probability of failure, right? So this is one approach. We can also use the tree diagram, right? So here at the roots, I say I have three options. Either I have high contamination with a chance of 0.2, medium contamination with a chance of 0.3, and low contamination with a chance of 0.5. If I have high contamination, probability of failure given high is 10%. So this number, right? So if I want to see what's the chance of ending up in this branch, all I have to do is to multiply 0.2 by 0.1, which is 0.02. So this is exactly what I did here without this basically. So basically this path here is this number that I calculated, right, from the Venn diagram. So similarly, we can calculate failure given medium. So this path will give me the number here. And this path, failure given low, this path will give me the number here, right? And I simply add them up and I get the chance of failure, right? So the additions are here. So there's a 23%, 23.5% chance of failure. Okay. So now we talk about another extremely important topic, and that's independence, right? We call two events independent. So for any reason, if if there's an overload of information, really try to pay attention, because again, this is important. And you can, go and watch the video again. But independence is an extremely important topic. Again, not just for this course, in my opinion, in your life, in helping you make decisions, it's a very important topic. So we call two events A and B independent if either of these conditions hold, right? So if one of them is correct, in fact, all of them are correct, right? So either if P of A given B is P of A, that means that knowing B, right? So it's always important to decode the mathematical equations into English words, right? So the first line means that knowing that B happened will not change the probability of A, right? So what is an example of that? Let's say A is the chance of getting the second flip, like A is a second flip head and B is the first flip head, right? Knowing that the first flip was head will not change the chance of the second flipping head, right? But probabilities that are not independent, for example, removing the marbles from the sack, right? If we know that the first marble was blue, the chance of second marble changes, right? Or similarly, knowing A doesn't affect B, or the third one, which I said is most of the time incorrect, right? So we see that the third equation here tells us that there's an easy way to calculate the probability of intersection, right? You don't really need to write P of A times P of B given A, right? Remember, we had another equation quite similar to this one. It was P of A and B is equal to P of A times P of B given A. So the nice thing is that this equation is always correct. But this equation is only correct if the events are independent, right? Which is a rare event. Usually events are not independent, right? So you can, of course, use this if the events are independent, but for sure you can't use this equation if the events are not independent. Okay, so some examples. I roll a die 4 times, right? If I get 6 in the first 3 rolls, it doesn't decrease the chance of getting a 6 in the 4th roll, right? These are independent events. Picking marbles from a bucket with replacement, right? Meaning that I have a bucket that has blue and red marbles. I pick the first one, I see it's blue, I put it back. You know, once I put it back, the fact that my first marble was blue does not change the chance of, you know, when I pick the second marble being blue or red, right? And of course, here, when I'm saying this, it means that I already know what's inside the bucket, right? I know that there are like 5, you know, blue marbles and 6 red marbles, right? It's not that it's like a closed bucket and I don't know what's inside. So I do know what's inside the bucket. Another example, you flip a normal coin 5 times. What's the probability of the 5th one being head if the first 4 are all head, right? So again, that probability is 1 divided by 2, because knowing that the first 4 flips were head does not change the probability of the 5th flip being head or tail. And this is called, the last one is called the gambler fallacy. So it's our intuition, unfortunately, is often wrong, you know, in many cases. And a gambler's fallacy is basically a gambler, like somebody who gambles like 10 times and loses, thinks that, oh, I've already lost 10 times, so this is my time to win. That's not the case. If you lose 10 times, the probability of losing the 11th time is the first probability of losing in the first round, because these are independent events. Let's see, what time is it? Okay, so we do have independence with multiple events, right? So if I have events 1 to event k, and if all of them are independent, to calculate the probability of intersection, all I need to do is to simply multiply the probability of each one of them. And remember that, again, this equation is incorrect most of the time. It is only correct if the events are independent from each other. Okay. So let's solve this question. Assume the probability that the wafer contains a large particle of contamination is 1%, and that the wafers are independent. That is, the probability that the wafer contains a large particle does not depend on the characteristics of any of the other wafers. If 15 wafers are analyzed, what's the probability that no large particle is found, right? So we know that the probability of containing contamination, so probability of contamination is 0.01%, 0.01 or 1%. So we want to calculate the probability that in 15 particles, there's no contamination, right? So I want to calculate the probability that there's no contamination in part 1, no contamination in part 2, no contamination in part 15, right? Since the question tells me that they are independent, I simply write it as P of C1 prime times P of C2 prime, P of C15 prime, right? So P of C is 0.01. That means that P of C prime is 0.99, right? So each one of these is 0.99, and there's 15 of them. So the answer is 0.99 to the power 15, right? So 0.99 to the power 15 is 0.86, right? So it's a good idea to look at these, right? So if the chance of, you know, having a contamination in one part is only 1%, then the chance of having at least one contamination in 15 parts is 14%, 1 minus this number, right? So as you pick more and more parts, the chance of having at least one contamination grows. Okay, so the very last topic that I will cover today, this is a very important topic. Today we covered many important topics. This is the last topic that we will cover, and that's called the Bayes theorem, right? So the Bayes theorem states that probability of A given B is probability of B given A times probability of A divided by probability of B, right? Why that is correct? To prove it is super easy, because probability of A given B is P of A intersection B divided by P of B, and P of this guy here, P of B given A, is P of A intersection B divided by P of A, right? So this P of A and this P of A cancel out, and at the end, this basically the right-hand side and the left-hand side are equal, right? Of course, P of B has to be more than 1, because if P of B is 0, then this doesn't have a meaning, because P of A given B is only defined if B can happen, right? So let's look at, I know that we have covered a lot of material today, and I know that your brain may not have enough room for one more topic, but let's try to basically focus for just 2 more minutes on basically this question. So we saw this question before. For some parts, we either have contamination or we have no contamination, right? Or either high contamination or low contamination. And remember, this is the one we drew, right? So we had failure here, and failure can happen because of either high contamination or not high, right? H prime, right? So from this table, probability of failure given high contamination is provided, that is 0.1. Probability of failure is also provided. Actually, no, probability of failure is not provided. We don't know what's probability of failure. All we know is probability of failure given H, which is 0.1, and probability of failure given H prime, which is 0.05, right? So to calculate probability of failure, we already did this, but it's always good to review, right? So to calculate probability of failure, I'm going to say probability of failure is equal to this part plus this part, right? So I already calculated the first part. Now I'm going to answer the second question, right? So to answer the second question, note that probability of failure intersection H prime is equal to probability of failure given H prime times probability of H prime. And that is equal to probability of failure given H prime is this guy here, 0.005 times probability of H prime, that's 0.8, right? So yeah, so that's some number, right? I have to use the calculator to answer that. As a bunch of zeros. Actually, we can do that. So that's 40. How many zeros? 1, 1, 0, 2, 3, 4. 1, 2, 3, 4. Okay. So this number here, probability of failure given H prime is so this number here is 0.004, right? Now, similarly, I have to calculate this part, right? And this part, probability of failure intersection H is probability of failure given H times probability of H. Probability of failure given, actually that one we already know, we wrote it here. So that's 0.1 times probability of H, that's 0.2. So this guy here is 0.02, right? So at the end, to find the probability of failure, all I have to do is to add up those two numbers. So 0.004 plus 0.02, and that is 0.024. We already calculated this number before. That's probability of failure, right? Now we want to answer question 3. What's probability of high contamination given failure, right? So basically the question tells me that we have a part that we know has failed. What's the probability that that part has a high contamination, right? For this, we have to use the Bayes theorem. So probability of H given F is probability of F given H times probability of H divided by probability of F, right? We know probability of F given H, that is 0.1. Probability of H is high contamination, it's 0.2. So 0.2. So always, when you use the Bayes theorem, the denominator is basically most time-consuming part to calculate, right? You saw that to calculate P of F, I had to add these two, right? But I already have it here, so I'm going to use it here. So 0.024. So that's it. Now I have probability of H given F. Okay. So Bayes theorem also applies to multiple events, right? So if I have K mutually exclusive and exhaustive events, so mutually exclusive means that no two of them have any intersection. Exhaustive means that if I have my sample set, E1, E2, all the way to EK, cover the entire sample set, right? So that means that probability of E1 union E2 union EK is 1, right? So that's the meaning of exhaustive, means that I have completely exhausted my sample space, right? So I have the Bayes theorem for, for that case as well. And again, you see that the denominator is difficult to compute because we have to add up many terms. So that's all I wanted to cover. It took a little bit longer than I anticipated, but that's okay. I can answer any questions. I'm going to stop sharing now. I can answer any questions that you have, and then I will answer remaining questions next week on Wednesday.